Okay, so in relation to series, infinite series, there is a really interesting, not interesting, well, no, it is interesting. There is a really useful notion called a Taylor series. So a Taylor series is a polynomial approximation to a function. And by that, I mean, suppose we have some function, I don't know, there. And suppose we don't know the global behavior of this function, right? It could be a very strange function. We don't know the global behavior of it. But we know the local behavior around some value c. Okay? And we want to model the global function, or we want to model the function at least around this point here, right? Suppose we don't even know around c, we just know the function's behavior at c, and we happen to have information about its derivatives, right? So suppose, okay, we know the function's value at c, so this is like f. And so it's like right here. So here's f of c. And then we also happen to know its derivative at c, its rate of change. And this is not uncommon to know, right? Like if you're like measuring something, it's not difficult to figure out how much the thing is changing over time at that moment, right? So suppose we know its rate of change, which means that we know the slope of the tangent line at that point. Okay. Now look real close around c. Isn't it the case, like if I highlight this function from there to there, like in that interval, that blue business on the tangent line right there, it more or less it's like matching up with the graph of the function, right? So why not make a polynomial that does that? For example, what about if I say let p of x equal to f at c plus f prime at c times x minus c. This is a function of x. This is a polynomial, right? It's just it's a degree 1 polynomial because that's a number, x. This is going to be approximating this function around c. Well, why is that? Well, what's the derivative of this polynomial? Well, that's a number, so that goes to 0. That goes to 0. It's just the coefficient of x, which is f prime c. So it turns out that if I plug in c, so the derivatives match up. Well, what's the function's value at c? Well, if x is equal to c, this goes to 0. That's 0. You're just left with c. So the polynomial agrees with the function at c, and its derivative matches the function's derivative at c. So this is called a Taylor linear approximation to the function. to the true function. Because around C, it's a linear function, right? It's just a degree 1 polynomial. And around C, it matches up at the value and it has the same derivative. It basically behaves like C. And this is, in a lot of times, is a very good approximation. I forget the notation they use for the error. I will use there's some error involved in curving use. It's not exact, but it's close. Especially the smaller of the neighborhood around C that you take, the better this is going to be as an approximation to the real function. Okay. Can we do better? What about if not only the first derivatives match up, but what about if the second derivatives match as well? What would that look like? Right? Can we make a polynomial if we were able to measure the acceleration of this function somehow? Can we make a better approximation, a nonlinear function? Well, we can. What about we make p of x equal to this? Why would we choose this to be another approximation to this function? Well, you obviously see, like, so what is P of C? Well, that's 0, we're just left with f of C, so they match up. So this new function is going to also equal f of C at C. What about the first derivative at C? Well, that goes to 0. The coefficient of x there is f prime at C. That 2 times that 1/2, but there's still x minus C, so this will be 0. That will be 0. You're just left with f prime of C. So their first derivatives match up. Well, what about their second derivatives? Well, so we take the derivative. So I'll just write out. So what is p prime of x? Well, that's 0, and then it's the coefficient of x, and then that 2 times that half goes away. We're just left with f double prime of c times x minus c. So that's why if you plug in c into the derivative, that goes away. You're left with that. If you take the derivative of that, that's a number that goes away. It's the coefficient of that. So we get the second derivative is always equal to the f double prime of c. So in particular, the second derivative at c is equal to the second derivative of f at c. So we see that we match up. If we just plug in c, the first derivative matches and the second derivative match. This is a second order polynomial approximation to that function. Now, in general, we can just extend this on forever and make them match up as perfectly as we want. So in general, we could say, if we were able to measure the third, the fourth, the fifth, the sixth, the seventh, so forth and so on derivatives at C, our polynomial would look like this. Well, what's the notation that your book chooses to use? This is the word. So it's going to be f to the nth derivative at c divided by n factorial times x minus c to the power n. So this is the Taylor series approximation of f of x at x equals to 2. It's basically just putting together a polynomial that always has the same higher order derivatives as the function that you're trying to model. Okay, so I think the best way to do this would be to maybe just pull up Python real fast and to show you just how good of approximation that this can be. Okay, so give me 1 second to pull up Anaconda. Let me share my screen. Go away, go away. Okay, guess I'll just make one here. Okay, I really need to organize my files. All right, so import numpy as in p, import matplotlib.pyplot as plt. Okay, so let's do a function that let's see if I can pick a good one. Let's see, suppose maybe, I don't know, I guess we'll just do cosine or something. Let me make sure. All right, so NumPy definitely has cosine. So, all right, so what is our, so P1, well, yeah, let's call it P1. So P1 of X. This would be our first order Taylor polynomial. So this, and we're gonna try to model cosine. So goal is to model cosine around x equals 2 or something. All right, so this is just going to return np.cosine of 2 plus the derivative of cosine, which is negative sine. Sine of 2 times x minus 2. Okay. All right, so I'm going to need some domain going here. So domain is equal to np.range. Maybe say start at we start at 0, go to 3, increments of like 0.25. And let's just look at a plot real fast. So plot domain. Actually, let me try something real fast. Yep, works. So np dot cosine domain. Let's just make this color equals blue. And then let's look at our polynomial. So dot.plot main P1 domain color equals red maybe. So already you see that our red line or red approximation is pretty close to the actual graph. In fact, let me make this like a little bit wider so you can see. Like look at in the interval around 2, this approximation is already like pretty much spot on, right? You see that?
Yes, sir.
So maybe let's make a second order approximation and see how well we do. So if I copy that, I'll say P2. So that remains the same, but now we need to look at the second derivative of cosine, which is negative. So first derivative is negative sine. Take the derivative of that, it's going to be cosine. So negative np dot cosine of 2. And we have to, so this has to be divided by 2. So whatever 2 times that times x minus c all squared. All right, so that looks like the appropriate second order. So let's look at the second order approximation. So now I'll just put P2 in there. Oh, I put C. It's 2. That's C. There. Where's the error here? So P1 was fine. Let me just see what's up with P2. Yep, something's off. Oh, there. There's not a, I need to multiply that. No. There. So this is the second order approximation, right? So if you compare them, well, actually, I can just do it all in one. I'll call this one green or something. So you see how our new approximation is curving more? It's a non-linear approximation. So let's maybe make another one. Let's make a third order approximation. Let's call it P3. All right, so we take the third derivative, it's going to be positive cosine. Okay. So, oh no, positive sine. So sine, get rid of the negative, and now we divide not by 2, but by 6. Yeah, 3 factorial. And then we cube here. And then let's see what happens now. That one. Now let's put P3 in there. Yeah, now look at that. So now that the third derivatives match up, look at how we're just like curving. It's because not only do the functions values match up, the first derivative matches, the second derivative matches, and the third derivative match. It's becoming closer and closer to the true function, right? And this would work with any function that you give it. It doesn't have, like sine is like a relatively smooth function. But any function that you give it, you can make these higher order approximations, and it will, if you could do this forever, if you could like continue this on forever, you would actually have very little error and be basically the same function, but as a polynomial. Okay, so there is a specific type of Taylor series called a Maclaurin polynomial. And all you need to know is that Maclaurin is when C is equal to 0. So if C is equal to 0, you have this Maclaurin, which I don't ever use that at all, but your textbook might ask you a few questions on it. It's the same thing. You just take C to be 0 for the Taylor approximation. Right, so if C is 0, it's just, you don't have to worry about putting in these extra terms. Just, it's like a simpler special case. But as far as like suggested problems in this section to look at and to play around with, 27 through 37. And there are like there are a few numerical problems here that ask to use a graphing calculator. If you can, just look over what I did with Python. If you have Anaconda installed, you can. It might be a good experience for you to like practice plotting. But you don't have to. You can just use a simple graphing calculator. But 27 through 37.